just a couple words about why this funny quantity, the discriminant of a multivariable function, why it has the power to tell us whether we have a local max or min or whether we have a saddle point. Why can it do that? First of all, where did this quantity even come from? Well, it comes from a determinant. So when we introduced the idea of the first derivative of a function of several variables, we got this sense of what the partial derivatives were, and they were kind of these individual, slopes, if you like. But then we were able to bundle all the first derivative information for a multivariable function together into a single entity that was a vector called the gradient vector. Right? So the gradient vector of a function of multiple variables is kind of the derivative. It has the power to tell us the slope of every tangent line to the graph at that point, just by taking a dot product with the direction. So in the same sense that the derivative of a function of several variables is a vector quantity, the second derivative of a function of several variables is actually better than a vector quantity. It's a linear transformation. It's a matrix. So the second derivative can be thought of as a matrix, and the matrix that it can be thought of is a matrix whose entries are exactly the second partial derivatives. Right? So the first entry in the upper left is the xx partial derivative, and then we have the xy, the yx, and then the yy in the lower right corner. Right? So that matrix is often called the Hessian matrix of a multivariable function. And so for a function of two variables, it's a 2 by 2 matrix. And so this quantity, this discriminant, is the determinant of that matrix. It's the product of the two entries on the diagonal minus the product of the two entries off the diagonal. Notice, by the way, that I've written fxy in one of these places and fyx in the other. As long as these second derivatives are continuous, the Clairaut's theorem of equality of mixed partials applies. And so those two entries that are on the antidiagonal are exactly the same as one another. And that's why we end up getting the square up here. They're both equal to fxy. And so when I multiply them together, I just get fxy squared. And so this discriminant is the determinant of this Hessian matrix. And so what is the determinant able to tell us? In linear algebra, we find out that it can tell us a number of different things, one of which is it tells us how a linear transformation changes the areas of regions when it transforms them. Areas are volumes, whatever is your top dimensional measurement of size. But more to the point, determinants can also tell us about the sign, sign, of the quadratic function that's associated with a square matrix. So backing up a step, I can think about something that's a little bit more profound than finding a linear approximation to a function, which requires finding a tangent plane to the graph. We can find a quadratic approximation to a function, which would be the quadratic function whose graph best approximates a function near a given point. And it turns out that just like with finding a tangent plane gives us a linear approximation, finding a quadric surface that closely approximates my function gives us the best quadratic approximation to a function. And the way to do that is take the tangent plane, whose graph is given by the equation that we see at the beginning here, right? Z equals f of x naught plus the gradient of f at x naught dotted with x minus x naught, and then add to that this quadratic function over here, which is half of x minus x naught dotted with the Hessian matrix applied to x minus x naught. Right? And so the Hessian matrix defines a quadratic function in this way. Right? We take x minus x naught and we dot product it with that matrix multiplied by x minus x naught. And so what we learn in linear algebra, and we don't quite get to it in our semester of linear algebra, but some linear algebra courses do, is that we can tell based on the properties of this matrix when the function, the quadratic function that we get by defining it in this way, is always positive or always negative. When this quadratic function is positive definite, that means that the value of this second order correction is always going to be positive for values of x near x naught, which means that we would have a local minimum point because all of these quadratic corrections that we're adding to the tangent plane, which would be horizontal at the critical point, would have the effect of going upwards, right? And so we must have had a local minimum if this quadratic correction here is positive definite. Similarly, if it's negative definite, if the value of x dot product matrix x is always negative for values of x besides the 0 vector, then we would be at a local maximum, because the quadratic correction we're adding to the horizontal tangent plane would bend it downwards. And only in the cases where this function is indefinite, where this function x dot product matrix x is positive for some x's and negative for other x's, that means that we're not uniformly bending my horizontal tangent plane just upwards or just downwards. We're bending it upwards in some places and downwards in others, and so we must have a saddle point. And so for functions of two variables, all we need in order to guarantee that this matrix is positive definite is we need to first of all guarantee that its determinant is positive. And once its determinant is positive, it'll be positive definite matrix if the first one of its eigenvalues, so there's another linear algebra word that I'll throw out there, the first one of its eigenvalues is negative. So maybe the quick summary is this, that my quadratic function defined by a square matrix is positive definite, so we're going to get a minimum, if all of the eigenvalues of that square matrix are positive. And all the eigenvalues of a square matrix, a 2 by 2 square matrix, are positive when I multiply both of them together, I get a positive number, right? And when I multiply the eigenvalues of a matrix, I get its determinant. So that's why we need the discriminant here, this delta, to be positive. And I also need one of the eigenvalues to be positive. And if one of the eigenvalues is positive, it turns out that this first that the first entry, the upper left entry, being positive is sufficient for that. Similarly, for a local maximum, I would need my quadratic function defined by the Hessian matrix to be negative definite, which means all my eigenvalues need to be negative, of which there are 2. And so when I multiply 2 negative eigenvalues together, I get a positive quantity, which is the positive determinant of that Hessian matrix. And then if the first upper left entry of that matrix is also negative, then it's sufficient to show that all the eigenvalues of that matrix are negative. So linear algebra is really what powers this classification, and that's where this discriminant comes from. It's just the determinant of the Hessian matrix, which is the second partial derivatives of my function. You might ask, well, this is how it works for functions of 2 variables. What about functions of 3 variables or 4 variables or 10 variables or something like that? It doesn't seem like these 2 tests are going to be enough, and you would be right. These 2 tests are not enough for functions of more than 2 variables. We would need to know more. We would need to know, again, the one invariant criteria for this is looking at the eigenvalues of this quadratic matrix. If all of the eigenvalues are positive at a critical point, then that means that my function is concave up in every single direction. And so we could just find the eigenvalues of the Hessian matrix and verify that they're all positive. That will give me a local minimum. Verify that they're all negative. That gives me a local maximum. But actually finding eigenvalues is often a challenging problem. It involves solving a polynomial equation in the entries of the matrix. That is something that we will do toward the end of the semester in linear algebra this summer. But in general, it's a polynomial solving problem, which is very often challenging and very often needs numerical methods, especially in dimensions 3 and higher, in order to be able to solve. And so there are other tests for positive and negative definiteness that, again, use determinants along the way. So in the 3 by 3 case, you would check the upper left-hand corner. Let's say we want to find if it's a local minimum. The upper left-hand entry would have to be positive. That's the fxx partial derivative. And then the upper left 2 by 2 matrix determinant would have to be positive. So that would be fxx fyy minus fxy fyx. But then also the determinant of the 3 by 3 whole matrix would have to be positive as well. And so that 3 by 3 determinant involves the z partial derivatives in there as well. So there are other tests to do that too, but it does become a more challenging process of classifying critical points in higher numbers of variables than 2, just because there's more conditions to check. And I think most multivariable calculus textbooks don't do optimization problems for functions of 3 or more variables for that reason. It's not that it's sort of mathematically more challenging, it's just kind of mathematically a little bit more tedious because there's more criteria to check.